Hello, welcome to Lab 17, Part 2. And we're going to kick right off question 17 and asks you to look at figure 17-4, which is right above, and talk about, in the Northern Hemisphere, what radiative forcing seems to have formed and how does it compare from the simulation. And so above, the observed is the solid line and the simulation is the dotted line. So we have a set of two pieces of data. And they just ask you to talk about how do they compare, where are they accurate, where are they a little bit off. And so write a little comparative, like pick some dates and times and be like, simulation seems to be kind of more accurate from this point on, or it seems very inaccurate, or there doesn't seem to be any match in this year, and kind of pick it apart. Give yourself like 2 or 3 things that show that you can see observations in this figure above. So, use your figure and give me at least 2 observations from what you're seeing. And then from there, I'm going to highlight some notes in the paragraph simulating future climate change, and then we'll talk about the next question. Okay, so for the next set of figures, we're going to be looking at modeling for the future. So all the previous questions were to line up how do we see the data, what are we basing our science off of, so how are these models going to work for future? And it starts out right away by saying that we can simulate relationships between what's going to happen in temperature compared to these changes that we're making to the atmosphere concentrations of greenhouse gases, so methane, carbon dioxide, carbon monoxide, nitrous acid, so on and so forth. And on the next page, there will be a diagram with different modelings, and we're actually going to be using 3 different model simulations, and each one of them are going to estimate and model things differently. And that's because we can't account for everything. So on the next page, you're going to see data. It's derived from the Model for Assessment of Greenhouse Gases Induced Climate Change, or MAGIC. And MAGIC is the scale. It's the go-to whenever we try to do anything in the sciences. So this is the actual data. And they're going to show you the estimates, so the old estimates that they have, and the projection for the future. And so everything up to the 90s has taken place, and they know that, and then everything after is projected future all the way up to 2100. And the first question that they're asking is to describe the magnitude of radiative forcing in the period of the 90s compared to the projection of 2000. So you're doing a comparison between 90s and the 2000s. And I would say do them within each projection. So on the next page, I should probably flick pages so that you can see it. On the next page, you're going to see different data markers. You see different data markers, and it's the one on the top we're looking at here. You have different data markers, and it shows the projection of years. And so this is our future projections of forcing, and you have some different pieces of data to determine that. So each one of these have a different projection. The first one, A1F, that sucker is if we continue doing exactly what we're doing, population growth, concentrations of CO2, no diversification of our portfolio of how we get energy. And so this one, I can see I have a concentration change from the 90s, which is this year set, which we already know the data, that's true. That's about 1, so 1 degree is what we're talking about. And we can see a change all the way up to an 8-degree range, right? So for this example, I have all the way up to 9, 1 minus 9, 8-degree range. A1B is like a comfortable transition to change. And so this sucker, when I look at that, 6 minus 1, I have a 5-degree range. And 550 parts per million is a projected goal change in range. And so that sucker, I can see I would have a temperature change of 3 degrees. And so those are my projections. Write, each one in a little category and say, range for A1F is an 8-degree range, so on and so on. Give yourself your relative forcing, give yourself the change in that question. So question 8, by examining A1B scenario in the latter half of the 21st century, what conclusions can be drawn about the relationship between CO2 emissions and the resulting atmospheric concentrations? Just answer the question. There really isn't much else to say. And then question 9 asks you stable atmospheric carbon dioxide at 550 parts per million. If we were to stable it out at that part, what would be our implied future emission scenario? You know, basically what can we expect in our central? And this one, question 9, asks you to observe down here, and what they're talking about is how much we would have to cut our emissions to. And so if we did the CO2 concentration cut, the emissions change would have to be a drop of that. So you're just reading, you're just reading and writing down the answers. There isn't much to explain or show. It's just question 9, you're now looking at the figure below to answer your questions. Okay, so now we're going to talk about sensitivity and feedback loops. Now we're getting into feedback loops, where positive feedback loops means a change that will create more change, and a negative feedback loop means this change will cause no change at all. And they're talking about why they pick 550 is because that would be a doubling of our pre-industrial levels. And so our pre-industrial levels was 280 parts per million. We are currently at 390 parts per million, and a doubling would be around 260 parts per million. We know if we were to double that, we would cause naturally a warm-up that would increase the amount of energy in the environment to 3.5 or 3.75 watts per meter cubed. So if I took atmosphere and I took the amount of energy in that atmosphere, it would increase by 3.75. And that is without any feedback loops. So without any clouds, without any snow, without any ice, without any albedo, without any changes to the natural environment. The next set of questions, 10, 11, 12, 13, ask you what type of feedback loop, positive or a negative one, would you expect if we were to put you in a certain scenario, like take all the snow and cover the entire planet in snow, or take all the snow and ice and melt it away so that there is no albedo. So we know it is going to get warmer, but what might this change do? What might taking all the snow and ice away change or do to the environment? Tell me if it would be a positive feedback loop or a negative feedback loop, and then maybe what you think would happen. You know, and this is educated. You're going to use your educated guessing as to what you believe will happen, but obviously we don't know for sure. So you have to be logical. You can't say aliens will come down to this planet and take over. That is not logical. But you can be creative. You don't have to be straightforward in your answers. But once again, questions are pretty straightforward. Positive or negative feedback loop, and then what do you think will happen for those questions? All right, so now going into note taking, because you're going to answer those questions, and I'm just going to give you the notes. For the future questions, you're going to be looking at figure 17-7, and you're going to be playing with the same projections that we saw. So the 3 simulations that we saw on the previous page, they're going to reintroduce you to them on the next page. And so the bars to the right of the diagram show the range of temperature change to 2100, and you could see the low change to the high change in actual temperature range. The solid bar on that image to the year 2050 shows the range projected temperature change and a 6-watt radiant forcing. So this is like double that, which is what we would expect to happen in scenario A1B. So once again, we're looking at the scenarios on this page, and you're looking at scenario worst case. This is that one. This is scenario most likely going to happen with no political action. And best case scenario, we hope we really do this because we want to survive on said planet. That's what we're talking about in our simulations. The last set of questions, 14, 15, 16, are based on looking at this modeling, this change in temperatures in over the next 100 years, and actually 90 years at this point. We're really looking at kind of the 90-year mark. You don't have to be too crazy with your answers. You can basically answer accordingly because they're going to ask you at like a 25-year interval and a 50 and 100-year interval.